Welcome back. In this part of the tutorial, we're going to create some walking paths. So we still have our terrain right here, and we want to automatically place some paths that follow the terrain in a mostly natural way. So what we're going to do first is actually make a network of where paths are likely to be. So to do that, first we're going to flatten the terrain using a wrangle. So we're going to store the current elevation using this, and then after that we'll flatten the terrain. So now every Y position is at 0. And after that, we can actually start to remove some points that are too steep, because we still have the slope attribute stored in our attributes. If we middle mouse button click, we still have slope, even though we flattened our terrain. So let's do that. So let's make it a check with a parameter so we can adjust which slope to remove. In this case, we're going to remove points. Right now, it should not remove anything, but as soon as I add the parameter using the button again, we should be able to start removing, yes, the steep parts of the terrain. In our case, I think a 0.2 value should be okay. Remove steep slope. Excuse me. We will generate a group of all the unshared points currently, because later on we want to check where the edges are of the pathable areas. So I'm going to use my prepared unshared group. There we go. So now we have points for all of these. And now, because we have this group, we can remove all the current primitives using a add sub. Because it's a point group, the group will be maintained. And now we're going to create a path network. Because we're going to use the find shortest path node. And this node prefers to actually have open primitives instead of closed primitives. And yeah, so we're going to create some edges going from every point to every nearby point. So again, we'll use a wrangle for this. Create path grid. So what we're going to do is create an array of all the nearby points. And that will be from 0, the first input from the current point position within a range and a maximum amount of points. And we'll initialize some other variables. Number of points equals the length of the points array. Initialize that primitive variable and an I index variable. So for I equals 0, while I is smaller than the number of points, you keep adding 1 to the index. And now to avoid actually creating double primitives, we will only create a primitive if the starting primitive is lower than the end primitive. So it will create only an edge in this direction, but not in this direction. So to do that, we're going to use the continue command. So if the current point is lower or equal than the source point that we're using to find the array, pardon me, we're going to continue. Continue. So that means basically skip the rest of the code in this loop and start over with the increased index. So if we're not continuing, we're going to create a primitive, add prim, polyline, and we'll add 2 vertices. One will be, oh, sorry, R, call it BR here. Oh, let's not do that. So we'll add a vertex to the BR primitive, and we'll start with the current point number, and then we'll add the other one as well. Okay, so that should not generate anything yet because the range is 0. So let's fix that. Yeah, because how a grid should be 1 meter between every 2 points. So I want to create a grid that goes in all directions to a maximum of, say, 24. Okay, now it starts cooking. There we go. And now we actually have a grid that crosses in most directions. So from every point, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 16 directions. And because we're not using just the 4 directions, the result of our pathfinding will be a lot more smooth. Okay, so let's bring back our grid to the original elevation. That's why we saved it before. Let's quickly save it and press G to bring back the network to its original height. And this is the reason why we did flatten it. So basically this range is only the 2D distance. If we kept the terrain at the original height, the grid would be a little bit more sparse. Because now it will only, yes, sure. Yeah, so now you see there's a lot less connections because the distance in Y is actually larger than it would be normally. In theory, this could also be a good way to sort the edges and only have I have like less connections over the steep areas. And also I'm thinking, yes, this of course needs to be bigger than, not smaller than. Because right now we're only keeping the steep areas, but we actually want to keep the flat areas instead. Okay, so yeah, that's what we want. Okay, let's put it on manual update mode, re-enable that, and re-enable that. Just to quickly see the difference. There shouldn't be like as much difference as before, but there might be some extra connections, like right here, for instance. Okay, so it's mostly the same anyway. But let's continue. Okay, so the next step is to actually get rid of these small islands. So to do that, I'm going to add a connectivity sub, which we'll put on primitive. And now we're going to do some examples of how you can remove these islands. And we'll start with the slowest method, apart from the all for each shop, which is even slower, of course. So for each connected piece, it already added one of those. So in our case, we want to definitely run over primitives. Yes, that seems correct. That will still be fast. Not as fast as I hoped. But basically, it's not doing anything right now because, yeah, it's just looping over all the things. And then we're merging them at the end. So let's add a wrangle to check if the current class is actually too small or not. We're going to go to detail and we'll fetch the box size, get the box size from the first input, and we don't care about the Y size, so we'll flatten it. So now we only have information about the X and Z bounding box. And then we're going to create a detail attribute, remove class max. Yes, of course, yeah. So we're going to get the maximum size, so either X or in Z. Because the stuff with this actually is smaller than in class axis length. Yes. Yes. There we go. And now we're going to add again the attribute, and we'll say if it's smaller than 100. Then we're going to delete. And we're going to delete by expression. And for the expression, we'll use our detail function. And we'll look at the attrib wrangle for. And we'll come on. And we'll look at the attribute that we just created. And that makes sense. And it will be 0 with the first index, even though it's just, only like one integer, so it should always be index 0. Let's also rename it small island. There we go. And create small islands. Okay, so if we start to connect this, after some cooking, we should get rid of all the small islands. But yeah, as you can see, it takes a while for this to cook. Yeah, Okay, there we go. So now the result is much more clean than before. Yeah, so we got rid of all the small areas. And of course, you can just tweak the axis length that you desire. So, but yeah, you saw it was a bit slow. So that's actually because if you use a delete node, you kind of forced the entire geometry to regenerate. And in our case, we don't really care about the geometry. We just care if it exists or not at all. So what we can do is just copy paste this and use a switch node. So switch, and we'll add a null node, and then add input, and then instead of there, we'll actually do that. And because we made the null the first input, we actually have to revert the result. So if the island is too small, it will be 0, otherwise it would be 1. Okay. So also it's a good idea to show for all nodes in this case, so we can actually see that these nodes actually reference each other. And now we can start comparing and see this should be a bit faster than before. Yeah, so that's already a bit faster. But because we're using the new for each loops, we can actually also start to compile this. So let's do that. Copy paste it again. We'll add a compile block. There we go. I'm going to quickly save, because right now this most likely will not cook. Yes, there we go. And so if you minimize button click, there is a compiled node during execution, and that error exists because what we're doing here is actually referencing this node by name. And if you're using a compile block, you actually need to use a special way to access other nodes. So this is actually done using the spare input. We're going to copy paste just this, and then look carefully at what happens in between here. There's now like an extra connection that goes between the two nodes. And now instead of this name, we can specify -1, and now it should work. And yeah, it starts cooking. So yeah, that should be even faster than before. So just to quickly, so basically, if you hover over the inputs, spare underscore input 0, refer to this expression as -1, such as endpoints -1, which is what we did here. Okay, so let's save that again. Okay, let me quickly look to the next step. Okay, yeah, so what we're going to do now is going to look through all these networks and try to identify sort of where the center line is. So we're going to use a trick for this using the pathfinding software, which is find shortest path. Okay. And this is actually where we're going to start to use the unshared group, which we saved here. So for this trick, we're actually not going to output the paths, and we're going to go from any start to any end. And this will generate just a single float attribute, which will be the cost, for every point towards the from the closest starting point, which will be the unshared group. But in our case, actually, we also want to use the ref point number because we can do an additional trick to skip some calculations later. Okay, so if we do that, and we'll add a color sub just to quickly show you what we just did. So if we use ramp from attribute and say cost, there we go. Oh, no, not plus 0. Right, there we go. So yeah, now I can start actually, and you can actually see that the gradient goes towards the center in a sort of straight skeleton manner, especially if I would disable the normals. But yeah, like right now, we just need to find the points where there is basically no next point. So all the highest numbers relative to the starting positions. And we can use the previous point for this. So if we would visualize that, add a new visualizer, marker, ref point, ref point, and ref point. We should be able to see, yeah, there we go, that these all have like previous points, but the starting points don't, because they don't have a previous point, they're the start position. Okay, so what we can do is actually use a copy, attribute copy sub, and we actually need to yeah, so we need to actually store the starting position, or like the starting point number. So I ref point equals ptnum, save point ref, and we'll create another attribute, create attribute, there we go. And this will be a point, integer, 8-bit should be enough. And we will call this as ref point. And the default is going to be 0, and the value is going to be 1. So now what we're going to do is copying the ref position, the ref point, towards the previous point. Because in the attribute copy, there is a match by attribute. And we can actually start to use that. Quickly check, yes. So what we're going to save here is the has ref point. Yes, of course. And here we actually, well, I guess we can just use that instead. We're going to call it ref point. So now we are copying the original point number on the previous point number. And that has as an effect, let's add a quick color again, that any point that did not have a previous point will now be a different attribute than the rest. Okay, so let's disable that. Okay, so it doesn't work just yet. What's not yet? Breathpoint. Yes, needs to be breathpoint as well. Yeah, so there we go. So yeah, now we can clearly see that it starts to build some clear lines in the middle of our geometry. And these will be the guide paths that we're going to use to generate our paths, basically. So let's remove all the points that are of no interest anymore. So we can just set it to points, and we can say as ref point equals 0. We don't care about anymore. Oh wait, we do care about this one. We don't care about. There we go. Okay, so in the next part of this tutorial, we're actually going to start cleaning up all these networks again and remove all the extra lines that we don't really care about. We just want to maintain the large networks. Okay, see you there.